Our first speaker is Dr. Anthony Fox from the University of Cambridge. Dr. Anthony Fox studied computer science at Swansea University, and his thesis was on the correctness of microprocessor designs. After a short stint at Della, now Kinetic, he joined the Cambridge University Computer Laboratory working for Professor Mike Gordon. Recently his focus has been on designing and using a custom ISA specification language called L3. And the title of the presentation is Applied Theorem Proving, Modelling Instruction Sets and Decompiling Machine Code. So I'm going to hand over to Anthony now.
Okay, thank you. Well, many thanks for the invitation.
Check that works.
Yes, it seems to work. So there's going to be two main parts to my talk. The first part is actually on the specification side of things, specifying instruction set architectures. And the second part is, well, what do you do once you've got this specification? And the application we're going to be looking at is the verification of machine code programs through the use of a decompiler. So a bit about instruction set architectures to begin with. Many of you know there's lots of them, and they're big, complicated things. So the reference documentation for these things usually runs into the thousands of pages. The latest ARM V8 documentation is around about 3,000 pages in length. So there's a lot of material in there. 3 or 4, maybe, yeah, maybe. Yeah, and it's getting larger and larger. So that the current one actually has a V7 pass and then a separate V8 pass. And they're both quite sizable chunks. I mean, there's a lot more in there other than just the instruction semantics. But even just the instruction semantics part is very sizable. And then the instruction semantics is usually described using some form of pseudocode. But this pseudocode varies considerably from one reference manual to another. So ARMS is actually relatively good. It's actually quite detailed. You can almost sort of directly translate that into some sort of programming language. Whereas if you take the x86 Intel's documentation, this is very sort of loose and it's got a lot of sort of English text in there as well. In terms of official formal semantics for these things, they're not available, and certainly not in the public domain. So in-house, they might maybe be written in some sort of hardware description language or something like that, or various ad hoc things might be done instead. So what might you do with a formal ISA model? Well, traditionally they've been viewed as perhaps being a golden reference model. So if you're doing some sort of hardware verification or you're validating some code, an emulator perhaps, you need something to compare it against. And if you've actually formally specified what your instructions do, then you can use that as your reference. But another use is that you can actually, having specified what all of the instructions do, you can start reasoning in a very precise way about the meaning of programs. So if you've got a machine code program, you know precisely what it does to the state of the machine. And it's this second case that our group are currently most interested in. Formal verification of programs by the in a theorem prover via decompilation of machine code. So how might you go about formally specifying an architecture? I mean, this is a sort of simplified view of what you could potentially do, but so one thing you could do is just write it down as a mathematical description, or you could just write some sort of pseudocode or something like that. A mathematical description in itself, if you just publish it as a document, it has some uses. You're nailing down what the architecture is doing, but you can't really sort of directly use it. So if you actually want to run a program, it's not quite so useful. It's hard work to actually go from a mathematical description that's just textual. So you might consider using a programming language, so maybe a functional programming language. This again would potentially, provided you choose the right programming language, gives you a nice precise description of what's going on. And then you can actually run this. So you can then, let's say, take an ML program, you can run it and work out what your programs do. So the third approach is now if you've got a theorem prover, you can then specify it using the language or the logic of your theorem prover. So this was the approach that we used to use at Cambridge. So we used the HOL4 theorem prover, and we would then give a functional description of what each of the instructions does within the language of the theorem prover. Another theorem prover which is used for this quite a lot is ACL2. Warren Hunt is a big proponent of this. So ACL2 is sort of a cross between a programming language and a theorem prover. And it has the great advantage of it being actually quite fast as a programming language. So when you write your descriptions, you actually get a very fast emulator directly out of it. If you try to do the same in HOL, if you just write a whole description and then you do some rewriting in HOL and try and emulate what's going on, this is comparatively horrendously slow. So what I'll be talking about today is this fourth approach where I've actually developed a domain-specific language specifically for writing instruction set specifications, and I'll show how it relates to some of these other approaches. So as I mentioned before, previously we were actually writing these specifications directly in HOL4. The style of specification sort of changed over the years, but the same sort of underlying problems were there. So I developed this domain-specific language L3 simply to make my life easier. In particular, I wanted to be able to write the descriptions in a much more natural style, which was closer to the pseudocode that you'd get in the reference manuals. So the language itself is imperative in style. I mean, in comparison to actually doing these specifications directly in HOL, it becomes a lot more natural. So if you're declaring the state of, so you've got your registers and your memory, you can do this quite freely as you would do in an imperative language, as if they were global variables. Doing this sort of in HOL, the approach we were using eventually was to use this sort of monadic style, and there's a lot of heavy lifting going on just to keep all of this going, really. So we wanted to try and reduce the burden of that. It's worth mentioning that L3 is not really a hardware description language. It is very much specifically designed for doing these ISA specifications. And a lot of the features of the language are really there specifically. So the key point is that having written our specifications in this language, we can then export to suitable HOL4 code. And in fact, we can actually choose what sort of HOL4 code we want to generate from this specification. So there's two styles which are generated at the moment. Within the language itself, there's an emulator, so you can actually quickly test your specifications as you're writing them. But it also provides export to Standard ML as well. So if you actually wanted a faster emulator out of this, you can actually just generate ML code from this as well. So previously, when we had our HOL4 native specifications, we did have a route of essentially printing our whole functions out as ML code and doing it that way. But it was hard work, and it wasn't really a good way of doing it. So some of the features of this language, well, obviously an important thing is good support for bit vectors and bit vector operations. Another feature is the fact that it supports pattern matching, in particular pattern matching over bit patterns. So you can specify a pattern of bits with variables in various locations, and then you can match a value against that. And this is particularly useful when you're specifying what a decoder does. So this decoder is going to take some sort of machine code value and give you some sort of instruction out of it. And the language itself helps maintain an instruction data type. So when you specify an instruction, it adds that instruction to a data type of instructions, and this can then be the target for your decoder. And you can also write encoders as well, and it supports assembly code parsing. So if you're then wanting to take your instruction and work out what's the machine code value for that, if you're doing sort of assembly, for example, you can just, it allows you to write that function. There's also some sort of bookkeeping stuff in there for working with registers, with named fields and things like that. So one important thing which needs to be considered is how do you deal with all these sort of nasty, unpredictable and implementation-dependent features. And certainly if you're looking at the ARM documentation, it's littered with things which are described as being unpredictable. Other things are described as being unknown or don't care values, and there's also sometimes non-deterministic choice. Normally when you're formalizing these things, if there's a lot of non-determinism going on, you would often use relational models. But we're particularly interested in coming up with functional descriptions because we're wanting to be able to run and emulate the architectures. For the most part, ISAs are mostly deterministic. So we try and get away with writing functional descriptions. So how do we deal with some of these features? Well, it's often, it's the choice of the specifier as to precisely how they do these things, but the language itself supports a value called unknown, which can be of any type. So when this goes to whole, this goes to a constant in whole called arb. So this has some value, but you don't know what it is. If you're doing the export to ML, it will just make a fixed choice. So it will just give you a 0 or a false. So you need to be aware of this when you're doing your exports to SML, but potentially if you've got an unknown in there, it's going to be picking a value for you. If this is of concern, you might want to use option types instead. So this is where you can say, well, we've got some value or we've got no value at all. And you can write your specification on that basis, and you can specifically check whether or not this value is defined in the particular. Another approach which can be used, it's quite useful sometimes, is to have oracles. So you can say there is some function which is going to give you the result at a particular time, but we're not specifying what this function is, and it can be actually supplied later on, and it can give you maybe the sequence of bytes or bits, whatever, as is required. There's also a facility for model exceptions as well. So a lot of the ARM unpredictable stuff is actually modeled using an exception. So essentially this means that in the formal model, we either have a state, we actually know what's going on, or we have some sort of error that's happened. And we have this exception to say, well, some sort of error has happened, and we're not going to say what the behavior is for that particular case. So a little bit about the models. So that's the language. There are 4 main specifications in there at the moment. So the main one is this ARM v7 one. This was a port from our whole specification into L3. And it's more than just v7. It's very similar to the ARM documentation itself as far as it supports all of the architectures from v4 onwards. Most instructions are in there, but there's some advanced ones which aren't in there, so these neon ones. Some of the floating point ones aren't in there as well, but there is some floating point instruction support. And in particular, we don't attempt to model an MMU. All of that's considered implementation dependent. The memory is effectively just a big array, and we don't do address translation on it. We also have a simplified version of that specifically for the M0, so there's a separate variant of the ARM architecture, the M variant. One of the interesting features of that one is that we've added in cycle count information from the documentation, so we know how long each instruction takes. We also have an x86-64 specification. This is a relatively small in terms of coverage, but it's certainly a usable model, and it covers a lot of the core instructions that we're interested in. And we have a pretty complete MIPS 3 model as well, and that does have a model of an MMU. So a little bit easier to do with MIPS because it's a bit more standard, and a lot of stuff's done in software rather than. Having done these specifications, it's very important to actually try them out and actually make sure that they are what they're supposed to be. You don't have these sort of golden references we can compare our models against, so our approach has generally been to use development boards, emulators, your local PC, and actually just do a comparison for as many instructions as we possibly can. And various people have worked on this over the years. Just a few there, Magnus, Brian, and Mike. But I mean, this is always sort of ongoing. I mean, we have to be aware that potentially there could be problems in the model, and if something weird is happening, we possibly have to look at the model and see whether or not we have actually captured it properly. But I think we're reasonably confident that they're mostly right. Moving on to this machine code verification. Why might you want to do machine code verification? So one application is at the back end of a compiler. So there's a formally verified ML compiler written in HOL. And at the moment, this sort of bottoms out at byte code. And then at the last stage, we want to be able to verify that we can actually take this byte code and actually implement it on multiple architectures and prove that that last stage of the compiler is correct. And you might also want to verify any libraries that are associated with this compiler. Another big project, which is at NICTA in Australia, is the SEL4 micro-kernel. And Magnus Myrén has worked closely with them on that. And he's managed to decompile their entire microkernel into HOL4 functions. So that's quite a significant project. What do I mean by decompiler here? Essentially, the decompiler takes as inputs a machine code program. It then analyzes that machine code program, instruction by instruction, and constructs for you a native HOL4 function, just a pure mathematical function, which has the same semantics as the program. So it takes in the state, which would be memory and registers, and it will tell you what the new state is, memory and registers, for that particular program. Definition is completely independent of the specification itself. It doesn't contain the next state function for the architecture. But what it supplies is a separate certificate theorem, which proves that this decompiled function actually corresponds with running that machine code program. So you know that you can actually trust this function that it supplies you with. So the key point here is that it's abstracting away all the details about the architecture itself, and it's giving you something which you can actually work with in whole, which is this pure function. So here's a little example. So this top section here is some whole code written in ML. So this is giving a call to the decompiler. It's saying we want a function f1 that corresponds with this assembly code. So there's an assembly code parser as part of this as well. So I don't know how many people read ARM, but we've got 4 instructions here. The first is a move, then we've got a logical shift right, we've got a logical AND with one of the arguments shifted left, and then we're adding 2 arguments as well, and putting the result in R0. So we supply that, it then churns away, and it gives us this function here below, f1, corresponding with that. And as you can see, there's a pretty direct correspondence between this function and our original assembly code. So it's taking the original state of the registers R1 and R2, and it's giving updated values for R1 and R2, and we're also updating R0 as well. And we don't care what the original value of R0 was. So you can see this function f1 is just a very simple function. There's no reference at all here to the assembly code or the machine code or the model itself. It's just a pure whole function. But then our certificate theorem says if we run this machine code, that function is what's happening. So having done that, we could also consider another. So we've got on the left here, we've got our original assembly code program f1. On the right, we've got a second program f2. They have the same semantics. So this one's doing some rotates, it's doing some moves, ands, more rotates, logical shifts. And rather than the add at the end, we've got an exclusive OR instead. What we can do is we can run the decompiler on that as well. That'll give us another whole function f2. And what we can do in whole is just prove that f1 applied to those arguments is exactly the same as f2. So the approach in whole for doing these things is an interactive theorem prover. The user supplies a proof. And it's generally based around tactics. So here our proof applies 2 tactics. So the then in the middle is combining the 2 tactics. The first tactic, simp, basically does a simplification of our goal. So our goal is f1 is equal to f2 for those arguments. It then simplifies using the definitions of f1 and f2, which we got from the decompiler. That gets us so far. And what it leaves us with is an arithmetic property on bit vectors. So we can then apply our bit blasting tactic, and that finishes everything off, and we have our proof. It's worth stating that this was a very simple example, and it was just a straightforward sequential bit of code. We didn't really, there's no loops in there, there's not much control flow going on. So that's why the proof ends up being very, very simple. But the decompiler itself can deal with far more complicated code. It can deal with loops and branches. And provided the control flow isn't too complicated, it will work. But the decompilation process itself can be manually guided to deal with trickier programs. So that's it for now. The first link there is to do with the L3 language, specification language. And from there you can also see those 4 models for the ARM, the x86 and the MIPS. And if you're interested in details to do with the decompiler, that's Magnus's page from Cambridge. And if you want a demo or to look through the specifications, I can do that if anybody requests it.
Thank you, Andrew. So any questions? Let me pass you the mic so people can hear your question online.
Have you used your MIPS model in conjunction with the BlueSpec model of MIPS from the capability group?
Depends what you mean by in conjunction with.
Well, just have you worked together in any way, really?
We've been collaborating with them. So this person I mentioned here, Mike Rowe, is part of that project. And he's integrated our model into their test suite, and he's been doing that. Their aim is to try and boot Linux on the model. So the model is exported to Standard ML, and you can then compile it using Milton, which produces relatively fast code. We're getting around about 200,000 instructions per second, which we believe is enough to do something interesting with. So yes, we are working.
You know, in ARM architecture, there's unknown and unpredictable, as you pointed out. So let's say somebody implemented a CPU design, and then they generated binaries on that. And if you were to decompile them using your framework, would you be able to make any correspondences or lack of to the unknowns and the unpredictable?
So generally the decompiler will only give us instructions which are known to be predictable. So it will never, it will reject instructions which, so if it's doing something with the program counter, it's an instruction we're not comfortable with, it will just fail. Yeah, so certainly for ARM, any low-level details, I mean, the memory is just treated as a very simple map from addresses to bytes, essentially. And that's it. We don't attempt it. And certainly for this sort of decompilation work, we're not that particularly interested in this. I mean, if you're doing some hardware verification, that's really where you probably need a lot more of this detail to be there. But there's probably certain applications where some of this detail is required as well, particularly with caching and things like that. So, yeah, it's something which I think we're keen to work on potentially in future to get more and more detail in there. But it's at the moment it just gets in our way, having all this detail there. You could view it just as a nice clean abstraction. But dealing with address translation is definitely important.
Yeah, but for example, if you're trying to answer the question, does this piece of code actually invert a matrix? What you're doing is probably fine. Yeah. If you're asking whether this operating system is working correctly with this lock behavior or something, it's probably not applicable. Yeah, and clearly there will be cases where potentially the code could be failing because something under the hood is actually happening. So it's correct up to your assumptions and your abstraction, but that might be wrong, potentially.
The last question.
Ashish Sarbari from Imagination Technologies. Just building up on the last question. You know, Peter Sibel's group has been doing this relaxed memory modeling type stuff, and they did litmus tests to find bugs in implementations. Could this not be linked to what you are attempting to do here? Yeah, I mean, he is very keen on. So one thing, I mean, they've got a detailed memory model, and what they're wanting to, what they don't have is the instruction set semantics. And they're very keen to tie the two together.
Okay. Well, thank you very much, Anthony. Thank you very much for your talk. Thank you.